In this video we're going to be discussing a basic growth and also a decay model. These are exponential. We use the term growth and decay. We mean that something is growing by an equal factor, or increasing exponentially, or decreasing exponentially would be decay. For growth and decay, you want to think about things like a population, either of humans, animals, bacteria. You want to also think about radioactivity. So things of this sort, half-lives, these will all follow growth and decay models. Some are a little more complicated, but I'll just give you one of the basic ones here. So one of the basic models we're going to use for this is the output, which is f of x, is equal to a times b raised to some power x. So the trick with this is if b is between 0 and 1, so let me write that over here. If b is between 0 and 1, it's decay. And if b is greater than 1, it's growth. Now there are some other issues where you might have a negative exponent up here, and so you can analyze that function if you need to at that point. But if this exponent is positive and b is between 0 and 1, it will definitely be decay. If b is greater than 1, it's definitely going to be growth, and that'll be good for many of the situations we're going to be looking at in class. There's also another way to understand this, and I want to give this to you for a decay model. We'll use a different color. So for decay, you're going to have, let's call it, let's say it's a at t. A is used for the final amount, and t is time. So the final amount, or the final population, or weight or mass of a substance will be this function here, a at t. It's a function of time, and that's going to be equal to, and we're going to say this a is a p, or the principal amount, or the starting amount, and that's going to be times 1 minus a rate all to the t power. So this 1 minus r is going to give you some number that's between 0 and 1. That's where that middle part comes from. But you can see that the structure is pretty much the same. You've got some function. In this case, x is t. We just use t to mean time. It's still an exponent. And p is the initial amount. And then 1 minus r will give you your base. So let's write that down here as well, or on the side, so that you have it down. So p is the starting, or you could say initial amount. And then your r is the rate, and that's in decimal form. Most oftentimes this is given as a percent, so you got to change that into your in a decimal form. And then t is the time. And if you want to, you can write a at t is the final or end amount. And I'll give you the exponential growth one here. So we have the decay one, and the growth one is going to remain pretty much exactly the same, with one slight change. Instead of a minus sign, so 1 minus some number, would like a rate, like a percent, would get you right down here where b is between 0 and 1, and then if you add that rate, that would actually mean growth. So that's going to give you this 1 plus r is going to give you b being greater than 1, so that's going to be some growth here, and that's just r. And then t will be up here as well. So again, the regular old exponential function is some number out in front, and then a base raised to a power. And usually when you're dealing with decay or growth, what you're going to use is a formula just like this, where if you want to know the ending amount, it's equal to some starting amount, 1 minus or plus if it's growth, the rate, and then all raised to the t power or whatever the time is.